So today I want to talk a little bit about relationships. In all of my talks, I have a goal. The goal in this talk is no contradictions. So just tuck that away for a few minutes and we'll come back to it. So this talk is structured around this quote, and I've heard this years ago, and I have not been able to track down where I actually heard this from. I thought it was from a movie, Searching for Bobby Fischer, but the internet disagrees with me. But this is the quote: a novice sees only the chessmen, an amateur sees the board, and a master sees the game. And when we're talking about computer scientists, this is my own quote. Computer scientists are bad at relationships. We really are. We're very bad at relationships. So let's look at relationships. These are the pieces of our chessboard. A relation in math is an ordered pairs mapping entities from some domain to some range. It's distinct from a function in that the first entity does not uniquely determine the second. So a relationship is the way that two entities are connected. How are things connected? For any relationship, there's a predicate form of that relationship that determines whether or not the pair of values exists in the relationship. So if it's true, we say the relationship is satisfied or it holds. Right? So if our relationship is John is married to Jane, then the corresponding predicate is John married to Jane? Right? A constraint, then, is a relationship which must be satisfied, for which the predicate must return true. Well, what do we mean by must? What we mean is for some other relationship to be satisfied, this has to hold. So it's a little bit of a circular definition. So for example, the denominator must not be 0 for the result of division to be defined. So when we're talking about a constraint, we're always talking about two relationships. Right? The first is the denominator must not be 0, and the second is what violating that constraint would imply, which is that division would not be defined. So constraints are closely tied to the implication relationship. A implies B. This is the truth table for implication. Right? It's relatively simple. If we have A is true, then B must also be true, otherwise it resolves to false. If A is not true, it doesn't say anything about the value of B. So here is a simple, but it's a very incomplete notation, but we're going to use this as we progress through the talk, a very simple notation for visualizing relationships. Right? We have entities, and we have, which we'll draw as rectangles, relationships we'll draw as circles, and this forms a bipartite graph. The only way to connect an entity to another entity is by connecting the entity to a relationship and that relationship to the other entity. Right. So implication is represented with directional edges in our graph. So this is shorthand to say, given entities B and C, A is any entity such that the relationship R holds. So this is very similar to a function, except there could be multiple values of A that could satisfy that relationship. Relationships and objects. As soon as we have two entities, we have implicit relationships. And this is part of what makes relationships so hard and part of what makes playing chess so hard. Okay? As soon as you have multiple chess pieces on the chessboard, you have a bunch of relationships. And a memory space is an entity. Right? So the memory space of your machine is one entity. What that means is as soon as I have an object within that space, I have a relationship there, as soon as I just have one object inside of a memory space. And when that object is copied or moved, any relationship that object was involved in are either maintained, which means they still hold, or they're severed with respect to the other object. And so one way to think about that is everybody in this room is involved in some relationship with everybody else in this room. Don't tell your partners when you go home. Okay? You guys are all connected. Right? So you have a person to your left, a person to your right, a person behind you, a person 3 rows behind you, and 2 over. Right? You're all connected through some relationship. And if you move your seat, then your relationship with some other person in the room is either maintained, depending on what that relationship is, or it's severed. Right? So, and when an object is destructed, any relationship that object was involved in is severed, right? So if you're in a relationship with somebody 2 rows back and 3 people over, and you just poof disappear, then that relationship can't hold, right? Your empty seat is not involved in that relationship. Now, when we're programming on a computer, sometimes what we want to do is take a relationship, and instead of just having it be implied by how you guys are spatially situated within the room, we want to create an object that represents that relationship. That's an object that we say witnesses the relationship. It is not the relationship itself, it is simply a token to represent it. Right? So, because it's an object, right, one way to think about this concretely might be if you happen to be married, you might have a wedding ring. That wedding ring represents your marriage relationship, but it's not the marriage itself. So that ring witnesses your relationship. So if I copy that ring, or maybe I cloned me and my ring, okay, then we have to think about what that token now means. And there's a couple of possibilities. Either the relationship is maintained, okay, which would be me with my ring, and my clone with the ring were both married to my wife. Maybe I live in Utah. Okay. Or it could mean that the token ring is invalidated, which means that I'm wearing a ring, my clone is wearing a ring, but the relationship is defined as a one-to-one relationship with me, and so my clone is still wearing the ring, but that ring is now invalid. Okay? It implies a relationship that doesn't exist. Or the relationship could be severed, which means I could clone me, but the ring could not come along with me. Okay? And so now I'm married to my wife, my clone is not married to my wife, and my clone is not wearing a wedding ring. So those are the 3 options we have. Okay? And this includes if we're just talking about the ring itself. When an object is destructed, any witness relationship that object was involved in is either severed or invalidated. Right? So now we have this third invalid state that can come into play. So for this reason, we might choose not to implement copy or move on a witnessed relationship. Right? When people say that they have something like a mutex, which is not copyable, or a lock for a mutex, which is not copyable, of course, a lock is just bits in memory. Those bits in memory are copyable. But what that lock represents is a relationship, right? It's a mutual exclusive relationship with some other thread of execution, right? And so copying it, the expectation might be that it would still be in a locked state, but that can't happen. You can't have 2 locks for the same mutex. So in reality, what it would mean to copy a lock would be to sever that relationship, and you'd end up with a lock that wasn't holding anything. Or instead, you might choose just to say, no, you can't copy it because it's too confusing. Right? This is also how we get iterator invalidation at a distance, right? An iterator is a witness to a relationship, which means that if I change the object on the other side of the relationship, it can invalidate my iterator. So those are our pieces, a little introduction to relationships. These are the pieces on our chessboard that when we're playing the game of programming, we have to figure out how we're manipulating these relationships. So let's talk about the board now. The board is the structure formed by these relationships. Right? Mathematically, a structure on a set consists of additional entities that in some manner relate to the set, endowing the collection with meaning or significance. Right? So this is what brings meaning to our programs. So let's start with the most primitive relationship here. We'll step back a little bit. Since it's Halloween, this is my scary slide. It's completely white here, but this represents a void. It is both timeless and dimensionless. Right? So you've all just stepped into the twilight zone. There is nothing here. And into this space, we're going to have 4 bits. Now, you guys weren't paying attention, right? Because this is timeless, so these 4 bits were always there. But we have 4 bits in our dimensionless space. What do those 4 bits mean? Maybe this represents 4 bananas. Or maybe this represents the color blue. Or maybe it represents an abstract number 4. Right? The meaning we imbue on it is up to us. It's how we interpret the bits. What does that mean? We could say this collection of 4 bits could represent any value from -8 to 7. Maybe it's a signed 4-bit integer. And then we could have another set of 4 bits dropped into our dimensionless space. They've always been there, right? Trust me. That also represents a value from -8 to 7. So in this case, it would be 3. And now we can have a relationship between these 2 objects. So we can talk about 4 being less than 3. We can also have operations that are just looking at the bits, not the values, like hashing them. And that can tell us something about the values themselves. So if we hash these 2 values and the hashes are not equal, then that implies that the values are not equal. But our bits don't exist in a nothing void. They exist within a memory space. So within this memory space, there are other bits. Right? So what's the difference between that highlighted 0, 1, 0, 0 and the 0, 1, 0, 0 that's down below it? The only difference is the meaning that we as developers imbue on that object. As soon as we have bits in an address space, those bits have an address. They have a location, just like you guys have a position within the room. And that means that we can compare the positions of 2 objects. It also means that we can sort our 2 objects. What does it mean to sort? It means to order things such that their ordering in memory corresponds to their ordering as values. We can define other operations on how we deal with these objects in this space. So we can have addition. So that brings us to a definition of safety. An object instance without meaning is invalid, right? So just arbitrary bits in memory are invalid. So an object in an invalid state needs to either be restored to a valid state or destroyed. right? Otherwise, you have nonsense, an object with no meaning leaking throughout your system and making your entire program become meaningless. So this is related, if you're familiar with the book Elements of Programming, to the idea of a partially formed object. So an operation which leaves an object in an invalid state is an unsafe operation, right? It doesn't mean it's a bad operation. It doesn't mean that the bits are completely undefined. It means that at that point in time, the state of that object no longer corresponds to some other entity that it's supposed to correspond to, right? Some other operation is required to restore that connection to make the object valid again. std move is an example of an unsafe operation, right? When I move one object to another space, the object that was moved from is left in, according to the standard, a valid but unspecified state. Well, unspecified means without meaning, which means in this context, invalid. Right? So I always say the standard is a contradiction in terms in how they define validity. So they define validity different for move operations than they do for validity of iterators. So std move is an unsafe operation. That doesn't mean std move is a bad operation, right? In fact, it's an incredibly useful operation. It just means that the object that was moved from has no meaning. It's been stripped of its meaning. So what you have to do is somehow restore the meaning on that object or get rid of it, right? So you should be able to always assign to that object to restore the meaning or let it destruct. So C++20 has two new features specifically about relationships. Anybody know what they are? Louder? Spaceship operator. Oh, okay. I hadn't considered that one. Okay, 3. Anybody else? Concepts. Right, so we have concepts. One more. No, I lied. Contracts, but we don't actually have contracts. So there's one new feature specifically about relationships and the spaceship operator. So where do concepts come from? Well, concepts were first coined in this paper by Alex Stepanoff and James Dennert, Fundamentals of Generic Programming. That's pictures of the two of them. And here, what they say is we call the set of axioms satisfied by a data type and a set of operations on it a concept, right? So what are they saying here? A set of axioms is a set of constraints. So these are things that must be satisfied for a given object to satisfy a concept. Concepts, though, have their root going all the way back to this paper. This is a paper published by Tony Hoare in 1969, an axiomatic basis for computer programming. That's Sir Tony Hoare. Let's take a quick look at some of these basic axioms for concepts. So first thing that we define when we're defining concepts is the notion of equality. So two objects are equal if their values correspond to the same entity. Right? That's our definition of equality. What do we mean by the same entity? It's the color blue, it's the 4 bananas, it's the number 4. It's whatever we have in our head as developers as the meaning of the value. Right? So from that definition, we derive a set of axioms that define the concept of equality. Right? Equality is reflexive, it's symmetric, and it's a transitive operation. Okay. Now, those axioms define any equivalence relationship, not just equality. What makes equality unique is this mapping from the object to the entity, right? That's a one-to-one mapping. So axioms follow from the definition. They are not the definition themselves. A collection of connected axioms form an algebraic structure, right? Connected type requirements, an algebraic structure is a mathematical concept. Connected type requirements form a concept in C++. So that's what a concept is. What do we mean by connected? Well, we looked at equality. Equality is connected to copying. What does it mean to copy something? What it means to copy something is to create a new item, new meaning disjoint, right? Not connected to the original item, which is equal to the original item, okay? Which means represents the same abstract thing. So copy is connected to equality. So we can talk about the natural total ordering of things. The natural total order is a total order that respects the other fundamental operations on a type. Right? Why don't we have less than defined for complex types in C++? You could certainly define a comparison that would satisfy all the requirements for less than all of the axioms, meaning it would obey the trichotomy law and the transitivity law. You could just do a lexicographical compare of the bits that represent it, and you would get a less than ordering that would satisfy that. But we don't define operator less than because there is no natural total ordering, which means there's no total ordering on complex numbers that's consistent with, say, multiplication, okay, of two complex numbers. So here's an example. Integer less than is consistent with addition. So concepts themselves are quantified axioms. What do we mean by quantified? If you saw before, we said we had the expression up there for equality, and it had the math symbol for all, right? So a quantified expression is something that's for all elements, or there exists an element. Those are mathematical quantified objects. And as such, they're not very checkable on your machine, right? Can you show that for all objects that are equal, that axiom holds? Not unless you can somehow iterate all possible pairs of objects. So concepts in C++ work by associating those semantics with the name of an operation. So it's up to the developer to make sure that their equality satisfies the axioms. You have to do that outside of the language, typically in a proof. And what we say is that operator equal equal is required for this operation, right? In some place in the documentation it says, oh, and by the way, operator equal equal has to represent equality. So software itself is defined on algebraic structures. This is how software works. Now, I also wanted to touch on contracts. So contracts were cut fairly late for C++ 20. They were in and they were out. The idea of design by contract comes from Bertrand Meyer. The original publication, which I couldn't hunt down, was from 1986. This is a slightly later copy of his paper. This is the title. That's a copy of Bertrand. So applying design by contract. His work is also based on the work of Tony Hoare, an axiomatic basis for computer programming. So the two are very tightly related. Contracts were originally part of the Eiffel programming language, and they allow the specification of constraints on our operations. So we have preconditions, which are things that must be satisfied before we start a function. We have postconditions, which are things that a function guarantees it will satisfy, given that its preconditions are met. And then we have class invariants, which are relationships that will hold on a class after any safe operation has been executed on that class. Those are our class invariants. So contracts are actionable predicates that we can check on values, which means they run into some of the same problem with concepts, right? This is a quote from that original paper from Bertrand Meyer. In some cases, one might want to use quantified expressions of the form for all x of type t, px holds, or there exists x of type t such that px holds, where p is a certain Boolean property. Such expressions are not available in Eiffel. Right? So contracts is dealing with values and things that are very concrete, and it runs into this limitation where concepts ran into the same limitation and sidestepped this in a different way. Instead of saying we're going to deal with the values and check them up front, it said we're going to deal with the operations and let you as a developer prove that your operation satisfies this constraint. Concepts and contracts. Concepts are describing relationships between operations, and contracts describe relationships between values. But the distinction isn't always clear when you're programming. The comparison operation past std sort must implement a strict weak ordering relation over the values being sorted. Right? So the strict weak ordering relation is a set of axioms, a concept. But over the values being sorted is a precondition, is a predicate. Right? So it isn't always clear when you're developing where the line is between one and the other. Pattern matching is also closely related. Do we have any Haskell developers in the audience? I think one hand went up. So concepts are used as a compile time constraint to select an appropriate operation. Contracts assert at runtime if an operation's preconditions are not met. A runtime constraint to select an appropriate operation is known as pattern matching. Right? We don't yet have pattern matching in C++, although there's a paper kind of working its way through the committee for pattern matching. So this is what a concept looks like. So here we've got a function f, which requires that I is not less than 0. Okay? So the double requires there is because we're not saying we're requiring this predicate, we're requiring this expression is valid. So this was the proposed syntax in C++ 20 for a precondition to represent the same thing. And if we had pattern matching, I imagine it would look something like this. Right? Where now we're not talking about the operations on the type, we're talking about the value of the type to determine what matches. So there's one more relationship I want to talk about that's very important, and this is the whole part relationship. This is important when it comes to reasoning about our code. So the whole part relationship is a special relationship that allows us to build composite objects and treat them as if they were just a single object. So the whole part relationship says that our objects must be connected, that the connection cannot be circular, right? We can't have B be part of C and C also be part of B. So non-circular. It has to be logically disjoint. Okay? So we can't have this AB owning C, which is somehow shared with some other object which also owns C. They have to be logically disjoint. I say logically and not physically because if the value were immutable, you could actually share the value and it would still satisfy So logically disjoint. And it has to be an owning relationship, which means that if I get rid of the object, the whole thing goes, all of the parts of it go. So here, if I had a copy of our object and I destructed the copy, it would leave the original in place. So it's an owning relationship. So the standard containers are composite objects, and composite objects allow us to reason about a collection of objects as if they were a single thing. So this is why in some of my other talks, I talk about no incidental data structures. Right? Incidental data structures are when we have objects that are connected to other objects, and we don't have a clear demarcation between where an object begins and ends. We just have a morass of interconnected objects within our system. Right? So I don't want something like that. I want like a container object where I say, instead of having some implicit hierarchy, I've got an explicit forest here as a hierarchy. And that lets me think about that thing as being one entity as far as my relationships go. I also, in some of my other talks, talk about no raw loops. How many people have heard no raw loops? Right? So this was an example of a raw loop. A raw loop is a loop dropped in a body of code which isn't called out as being something specific with a name. Right? Why is it important that we encapsulate this thing and we give it a name? It's because a loop itself represents some form of a relationship. So what's the relationship here? It's a rotate. And rotate is a function, which lets me think about it this way. Okay? So that's our board. Everybody following so far? So now we finally get to the game. So architecture is the art and practice of designing and constructing structures. So this is the game. This is what we do as developers, right? We're architects of the systems that we build. We design structures. So let's walk through some concrete examples here. Here was a task that I was given at work. Write a piece of code to save a document every 5 minutes after the application has been idle for 5 seconds. Right? That's a pretty typical task. Any of you might be handed that in your daily job. So when I was given this, I thought, well, okay, save the document every 5 minutes. I know how to create a task on a timer, so I know how to do that part. So I can write that easily. So I'm not worried about that. Which leaves me with this. After the application has been idle for at least, well, it was 5 seconds. I'm going to make it n seconds, right? Because where did 5 come from? I don't know. So after the application has been idle for at least n seconds, then do something. My original task was to save the document, but saving is just a function. So I'm abstracting things a little bit here. So here's my first shot at writing this function. Right? What I do is I say, okay, I'm going to need to know when the application has been idle for at least n seconds. So I'm going to need some time point. Maybe I'll stick it in a global variable for the last time my application was idle. And then I'm going to need some function that can invoke an operation after a duration. So I'll assume I can get that somewhere from my OS. So I've got that. So now I'm going to write this piece of code. It says, after idle. I thought that was a pretty good name. So after idle, I'm going to execute my task by some delay after idle. So that's the delay there is where I'm going to plug in my 5 seconds. So I'm going to calculate a when. When do I want to execute this task? Well, I want to execute the task when my delay minus the current time minus my last idle time is less than 0. Right? So after my 5 seconds has elapsed, I want to execute my task. So if the 5 seconds has elapsed, or if the 5 seconds has not elapsed, then I'm going to recurse through my invoke after. I'm going to say, okay, maybe I'm 3 seconds into my 5 seconds, so in 2 more seconds, I'll check again. Okay? And so I'll keep chasing it until I've been idle for 5 seconds. And then I'll execute my task. So if my win has expired, if 0 is less than that, then I just execute my task right now. So this piece of code works. It's got a couple of small problems, but generally it's okay. Everybody follow it? Okay. So let's draw this. Let's draw the relationships for this piece of code. We're going to kind of ignore the recursion when we're drawing it, because that gets complicated to draw recursive data structures, right? You just keep going around. So we're just going to ignore the recursion. But generally, this is what we have. Right? Our 1 there is going to be where this structure recurses. Okay. We have 2 relationships going on here. We've got last idle, we've got now, and we've got delayed. And we combine those through a relationship. That was our subtractions going on. And that gives us our win variable. And then we're going to use win and our invoke after to invoke our task. So that's the structure of that. So what I see when I draw this is that I have 2 things going on. Right? And I have all of these external dependencies. Win is the thing I calculate internally. But externally, I need to know when the last idle was, I need to know when now was, I need to be supplied the delay, and I need to be supplied the task. So I really have 4 arguments going into this function. 2 are coming in as global variables. Right? And like I said, I have 2 distinct things going on here. Right? So let's look at the first part of that, which is when we calculate win. This is the expression. Now, if you're typically looking at a piece of code, you wouldn't think, should I refactor this 1 line? Right? It's just a couple of subtraction statements. But if I draw it out and I'm looking at the relationships, I think, well, this is something unto itself. What is it? Could I give it a name? Anybody want to hazard a guess what this thing is? Nobody? Rotate. Almost. It's circular. It's a timer. It's like a kitchen timer. Okay, that's what this thing is, right? What can you do with a kitchen timer? You can add time to it, and it counts down. You can't really speed it up without breaking it. And when it dings, when it hits 0, you need to go do something. So that's what this is. This is our kitchen timer. Okay? So we can add time to it, and otherwise it just counts down. So let's take another stab at this. First, let's take a look at the other part. So now we've got our kitchen timer. Now we realize that win was kind of a bad name, right? We had our variable called win, which was when we wanted to execute the thing. But if you were talking about a kitchen timer, you would be talking about how much time is remaining on the kitchen timer, okay? So now we're going to restructure this. So we're going to say, well, we've got our timer, that's t, and that's yielding our remaining time. Okay. And then we're going to combine that with our task to figure out when to execute it. Okay. So now we just have 2 arguments to this function. We've got our timer and our task coming in. And that gives us this operation, right? So now we're going to say, on expiration, we want to do something. We're going to take a scheduler. Okay. A scheduler is our invoke after some duration. our timer, which is counting down, and the task we want to execute. We're going to call our timer to get our remaining amount of time. And then we're going to decide whether or not we call our scheduler to reschedule this function recursively, okay, or we just execute the task now. So it's the same structure we had before, we just abstracted out the timer. Now the other observation here is before we could have our task execute immediately, like right there on the thread. And that's probably a pretty bad idea. That's how you introduce some weird bugs into a piece of software. If you say like, 90% of the time when I call this function, the thing executes in a queue at some point later off a timer, but every once in a while it just executes right now immediately, has some side effect and breaks my code. So to avoid that, we're going to make sure that we always schedule this thing within our scheduler. Right? Even if the timer's already expired, we're not even going to check the timer up front. We're just going to schedule it. So it's always going to bounce and execute in the same place. So that gives us this piece of code. This piece of code now has no global variables, no external dependencies, doesn't even depend on STD duration or STD time point. It doesn't care what your duration is or what you have a notion of a time point is, so long as I can schedule something to execute after a duration that's returned by my timer, whatever that is. I have those two things connected. Right? I don't need to pound include anything to get this code to compile and execute fine. So I've split out all of my dependencies. Now I have something that's cross-platform, that can run everywhere. So arguably a better piece of code. So architecture comes about by looking at the structures of the functions. And by looking at the structures of the functions, we can define better functions. As I said, onExpiration has no external dependencies. No STD chrono, no STD function. Doesn't need an invoke after or some last idle. The requirements are the semantics of the operations and the relationships between the arguments. It's completely self-contained. So let's take a look at designing another item. A registry. A registry is a container supporting the following operations. You can add an object and you obtain a receipt. So you get some token, right? You put an object in a registry, you get back a token. You use the receipt to retrieve the object, okay? Or potentially remove it from the container. And you can typically operate on all the objects within the registry. So a very common example is a signal handler. Right? I put an object into a signal handler, I get back some connection token. If I want to disconnect my slot from the signal handler, I can hand it back my token for the disconnect. And as long as it's in there, anytime a signal is sent, I'm going to iterate through all my signal handlers and call them all. So that's a fairly canonical example of a registry. Does everyone follow? So I took a look at my application. Almost every registry in the application, and there were actually several, look like this. They're an unordered map. Some of them were just maps, not unordered. They've got some kind of token, usually a counter, that they're going to use for a receipt. You can put something into the registry, and it's going to return the next token for it. Right? So it's just a mapping of receipts to the objects I put in. Given the receipt, my little ID token, I can remove it from the map. And then I can just iterate through all the elements in my map that match my token. Or just all the elements in the map, everything that's in the registry. Right. Sorry, I should have clicked through this. Forgot I had the arrow here. But we just said all of that. So this is my expression about how great this code is. Right? What's this a picture of? Right? You see these all over Russia. This is a code check. So this is my Russian code check algorithm. Now this isn't how Russian code checks actually work, but I'm from California, we don't even have coats, so what do I know? But here's the idea. If we recognize that our receipts here, we had a little counter, our receipts are ordered, okay? That's a relationship we can exploit. Coats are always appended, okay, with the stub of the receipt. What's the stub of the receipt? It's just a copy of the receipt with the same number. Then we can binary search to retrieve a coat matching our receipt stub, right? Because they're always in order. When more than half of the slots are empty within our code check, because we've retrieved the coats, we can just squish all the coats together to make space to put more coats on the end. Okay? So our coats are always ordered by the receipt stubs. And as an additional useful property, coats are always ordered in the order they were inserted. Okay, so if I'm iterating them, I'm always iterating them from oldest to newest. So for a Russian coat check, I can create a vector, which is a pair of my stubs, my size t counter, and an optional t, because I may or may not have a coat at a given slot in my coat check. Okay. And then I still have my ID here, which is what I'm using for my receipt and my stub, but I'm going to add this variable for a size, which is how many coats I actually have in my coat check, right? These are the optionals that actually contain a coat, the slots in my coat check that contain a coat. So I can append coats now by just pushing them onto the back of my vector, increasing the size. I added a new coat, increasing my receipt count, so the next guy gets a new receipt. So this is what it looks like. We put things in. Now, if we want to erase an element, what can we do here? We can find it with lower bound. Okay. And then, if it's not in the coat check anymore, we just return. Right? Usually a good property if you're trying to delete nothing or remove nothing from your coat check. It's fine. Coat's already gone. Somebody stole it, sorry. If we did find it, then we just reset the optional, which removes it. We decrement the number of items we have in our coat check. Okay. And then, if we have less than half of the slots in our existing coat check, the coats have been removed, then we make a pass and we compress all the coats. Okay. So let's take a look at how that looks. So we come along here and people claim their coats, and then we have more than half of the coats are gone. And so we just compress everything, remove it. So that's our erase operation. Everybody follow? And then we can continue to add more elements, right? And they'll get appended, and we always have the guarantee that our stubs are always ordered. So this code just continues to work. We can keep growing and shrinking. And then this is how we would iterate all the elements inside of our code check. Okay? Just a simple for each, not that hard. So here's the performance difference. This is our registry written with an unordered map compared to our registry written with a vector. This is the time it takes to iterate, or I'm sorry, to add all of the elements into our coat check. So considerably faster. Okay. The last item there is the amount of time it takes to iterate all of the items within the code check. Okay, so if you're in a slot signal handler, how long does it take to call all the slots? So the interesting thing here is that in this gap in the creation time, I can do 640 iterations of all the codes in my code check. Okay, so in the difference between the time it takes me to build my code check in an unordered map and the time it takes me to build my code check in a vector, I can iterate through all the codes in the code check 640 times. Now, what didn't I tell you? Do you believe me here? Is there a piece of information missing? Anybody? How many codes? How many codes are in the code check? You said 640 times. How many codes can I iterate over 640 times? Did that occur to anybody? It doesn't matter. Okay. I can generate the exact same comparison and I will get exactly the same numbers, plus or minus some small percentage, regardless of how many codes I put in the code check. Why? Here's the difference on how long it takes to add some number of codes to a vector and to my unordered map. The problem here is every item that I add to an unordered map is a new heap allocation, and that heap allocation takes time. And the difference between those two is linear, which means that if I add 1,000 elements in the time it took me to build it, I can iterate through all of those 1,000 elements 640 times. If I have 1,000,000 elements, I can iterate through the 1,000,000 elements 640 times. So relationships can be exploited for performance. This can be a fairly significant win. Understanding the relationships between the cost of operations is important. And that brings us to our final point, which is where we started here. We have a goal, no contradictions. What does that mean? Who here knows what double entry bookkeeping is? A couple of people who have seen my talk before. Okay, I'm kind of surprised because I think that this should be taught in high school. But double entry bookkeeping is an accounting tool for error detection and fraud prevention. Right? It relies on what's known as the accounting equation, which is assets equals liabilities plus equity. It's an example of equational reasoning, which just means we're reasoning about our system through equality. Sorry. Assets must be equal to liabilities plus equity. It was pioneered in the 11th century by the Jewish banking community, likely developed independently in Korea in the same time period. And in the 14th century, double entry bookkeeping was adopted by the Medici family and the Medici Bank. Who's heard of the Medici family? Almost everybody, that's good. So they're credited with establishing it's credited with establishing the Medici Bank as reliable and trustworthy, right? Because the Medici Bank adopted double entry bookkeeping, people trusted them. They put their money in them, the family rose to power. In fact, leading to one of the most powerful dynasties in history. Double entry bookkeeping was later codified by Luca Pacioli. He's considered the father of accounting. Just so you know, the person in the middle there is Luca Pacioli. He is probably a Euclid fan, given him diagramming Euclid solids. The person who's photobombing the painting here is just known as the perpetual student. It may be an artist known as Durar. We don't know. So double lettering bookkeeping. Every transaction is entered twice into at least 2 separate accounts. There are 5 standard accounts. This ensures that the mechanical process of entering a transaction is done in 2 distinct ways. Okay? For every transaction that comes in, we enter it into 2 accounts. It turns out it's always addition. You're always adding these things. And it's done in 2 distinct ways. So, which means that when you come back and you compare these accounts through the accounting equation, if it's not satisfied, we have a contradiction. So, what is a contradiction? It's when 2 relationships imply the same entity has a different value. That's what a contradiction is. When you're writing a unit test, what you're trying to do is write the same piece of code in at least 2 different ways and checking to make sure that they're consistent, right? You're checking to see if you have a contradiction. Relationships are consistent if they imply the same entity has the same value. Okay. So we can have 2 relationships which imply some entity. Okay. If they imply the entity is the same, it's consistent. Our books are good, right? We did the math in our transaction correctly. Our unit test passes. But if our 2 relationships imply the same entity has different values, then we've made a mistake. We have a contradiction. Now, every contradiction then has the same structure, but not everything with this structure is a contradiction. Right? So when we have a data race, it means we have 2 relationships which are implying an object has 2 different values at the same time. Right? We can stick a mutex in there which resolves the contradiction, okay, and gives us some unique value for our object. So, got a data race in your application. Developer, usually a fairly new developer, says, I see I've got a data race. I will throw in a mutex and I will fix that. Right? What does that mutex mean? Right? We've talked about the meaning of software. What does a mutex mean? Right? We know it means it's a mutual exclusion. Only one of these 2 things can win. But what does that actually say about our object? Right? What's now the meaning of our object after it's gone through this relationship? This is my face in the code review. Right? This is the equivalent of a novice player just moving the chess piece on the chessboard. Right? You're in check. I will move out of check. Right? Well, is that the best move? Are you just moving the pieces around, or are you actually playing the game? To play the game, you have to look at the system. You have to understand what the meaning is. You have to understand what these relationships mean, and then you have to understand how you resolve the contradiction. This is why I say no raw synchronization primitives. If every contradiction has that structure, and every race condition then is a potential contradiction, and just a raw mutex stuck in there doesn't provide meaning, that's a really bad primitive to use to resolve a contradiction. So no raw synchronization primitives. Use higher level abstracts to synchronize your code. A null pointer dereference. Right? The C++ specification, dereferencing a null pointer is undefined behavior. Right? So if I have this and my code crashes, It's because I have a contradiction between my code and the standard. The standard says I can't do that. I just did that. Contradiction, boom. So what does the novice player do? He sticks in a null check. Is this thing 0? Yeah, then don't do that. Okay, if P, then call the member. I see people fix bugs like this all the time. It usually ends up causing some other problem, right? Null pointers or optional objects have to be handled with some finesse. So we can think of nothing as a limit, and that's an important concept. Empty ranges, 0, etc. These are important things. But removing some section of code to avoid a crash is only likely moving a contradiction somewhere else in your code. So when I see developers do that, that's my response in a code review. Really? Did you think it through? So pro tip, use strong preconditions to move the issue to the caller. Sometimes it's very difficult to know what to do on a particular line of code, but you can kind of lift it out and make it the caller's responsibility to figure it out. So instead of having this, maybe change the code to that. So, two functions setting the same value through a shared pointer. This has exactly the same structure. Right? Possible meanings. Maybe the code's redundant. Maybe we have different aspects of the same relationship represented in disparate sections of code. So we have some value is A times B when A changes, and we also have the value is A times B when B changes. Okay, so it can come in two different ways. Maybe they're really different mutually exclusive relationships setting that shared value with some non-local control elsewhere in our program that guarantees we only go along one path or the other. Maybe there's some implied last-in wins relationship. Maybe there's some incidental algorithm and it's going to converge on the correct value. Maybe the property is not some simple property, but it actually represents a stream or a latch or something else. Or it's just wrong. Okay. Most likely it's the latter. If it's any of the former, your code doesn't tell me that. The structure of your code doesn't make that apparent. That's my reaction to shared pointers in a code review. No raw pointers. I define raw pointers not just as T star, but as a pointer, a shared pointer to any immutable state is a raw pointer. So, play the game. Consider the essential relationships. Learn to see the structure in your code. Architect your code, right? Don't just move the pieces around the board, right? Architect the game. Consider the game. This is my website, so you can find these slides here, and I will post a video or a link to the video once it's posted online for this talk. I work on the Photoshop team at Adobe, and Photoshop is hiring. I think we still have a couple open slots, so if you're interested, check our website. And if there's any remaining questions, I think I'm a little over time, but I will take them. Thank you.
Sean, thank you very much. Any questions? Any hands? Please raise your hand if you want to ask question. Поднимите руки, если хотите задать вопрос. Вопросы на английском задавайте, пожалуйста.
Hello. You've mentioned that you think, well, first of all, thanks for the great report. It was very interesting. At the very end, you've mentioned that you consider shared pointers very similarly as a raw pointer.
Yes.
How would you like a developer to create their primitives being pointers inside, but not being, making you this kind of face during the review?
Right. So the question here is, what's the alternative to shared pointers? The alternative is typically factoring out those data structures into some explicit data structure. So don't have a whole bunch of shared pointers in your code that really represent some hierarchy, but pull that out into a container that is the hierarchy. Okay, so that that container itself might be implemented in terms of shared pointers. It might not be. That's an implementation detail of the container, right? But all of the rules that govern what's shared and what's accessible is controlled then through that. So that's the number one thing. But it very much depends on the problem that you're trying to solve, what the solution is. If you think about it, we know from functional programming that we can always get rid of shared state. Right? So taking a more functional approach to the solution might be another way to solve the same problem.
Thank you. Thanks.
Okay.